Good afternoon, everyone, and welcome to the oral session 5.1, Synergies with Global Challenges. Today is the first time we use this room, and some of you have just come up to Hofburg today. So I would like to make you aware that in terms of health and safety, we don't have any drill planned for today. So if you hear the alarm, it's for real. So please proceed very calmly to your nearest exit. In this particular room, we either go all the way back through those glass doors and left, or through the door that you came in and follow the green signs for exit. So no drills today. So maybe we'll evacuate very calmly. Without further ado, welcome to this session. My name is Guillermo Rocco. I am the coordinator of the IMS division in CTBTO. My background is in seismology, even though I don't do much technical work per se today, but our division in CTBTO is in charge of building and sustaining the IMS network for CTBTO. So very, very exciting set of presentations we have today, and with some of this very useful data is put to use. That's all from me. I think I would like to introduce here to my co-convener, Professor Kathy Whaler.
Good afternoon, everyone. Really pleased to see such a lovely big audience here. As Guillermo says, we had a very wide range of abstracts, and choosing just a few for oral presentation was very hard, but we hope we're showing you some breadth of the use of the IMS data for many other purposes. I'm a solid earth geophysicist. My main research interests are geomagnetism and electromagnetic induction, so not so much about this kind of work, but I'm also the immediate past president of the International Union of Geodesy and Geophysics, and there interacted with many different areas of geodesy and geophysics. So I'm a little bit versed in the types of science that we're going to hear more about today. I think we're just still waiting for the setup. Can I encourage you to use the app to vote? It's not entirely obvious how you vote, but what you need to do is to open the session in which you'd like to vote, and then there is then an option on the right-hand side. So there's three headings. There's information, chat, and then voting. And then if you go to the voting part, then you can do that. And there will be a prize for best oral presentation. So I encourage you to do that. And obviously also encourage you to go to the e-poster session later in the week and then vote for your favorite poster as well. Are we okay with the... No, we still need to talk amongst ourselves for a few moments longer. I'm sorry about that. We'll introduce the speaker in a moment. Joe. Well, actually, you can vote early, vote often, as they used to say about voting in Northern Ireland.
Just a comment on that. I'm glad that you asked the questions, because this session is being recorded and it's being hopefully transmitted online. So anything we say, we need to say it in front of a microphone, so we can help the recording and the people online. So there will be people around us with microphones. So when the question time comes, just raise your hand and somebody will approach you with a microphone.
And there are some in the aisles as well that you can walk up to and speak.
How are we doing? Almost there?
And again, while we're waiting, you can use the app to put your questions into the chat there instead of raising your hand. Okay. So apparently we might be up to a little bit of almost 5 minutes more to wait. So it appears we are now ready to start. So I'd like to invite Danielle Harris from the University of St Andrews, where she's a Senior Research Fellow, to give her presentation. Did you explain about the black button? Yeah. Okay. Sorry, we just wait for it to be loaded. They've forgotten. You get extra minutes.
Time. I think they're supposed to start. Okay.
Okay, I'll get started.
Yeah, go for it.
Thank you very much. It's a pleasure to be here. Before I dig into my presentation, I do have a few acknowledgements to make that I didn't want to forget. So thanks to the Richard Lounsbury Foundation for supporting this effort. Our summer interns, Victor, Helen and Maddie, who did a great job this summer for the project, and obviously the data coming from the CTBTO. There's also another US Navy-funded project, Cortado, which I'll mention later in the talk, and you can see a whole team of people there. So this is very much not a solo effort, and thanks to everybody who's working on this with me. So the bottom line is wildlife monitoring programs are really costly, and I'm talking about whales, but there's a picture of an elephant there to remind me that this is a problem both in marine and terrestrial systems. And basically, we often want to know how many there are, and not only that, what their patterns are across time and space. And we often need these metrics for conservation and management purposes, of which there are many around the world. And so we're often looking out for cost-efficient approaches, and we sometimes call these platforms of opportunity, so instruments that are deployed not for detecting wildlife, but for other things but that we can make use of. And obviously, the CTBTO IMS is a fantastic example of a platform of opportunity from the wildlife perspective. So I'll be talking today about hydroacoustic data, and you can see the sites here on the map. There are other instruments within the IMS that have the potential to monitor wildlife, but I'll be focusing on the marine hydroacoustic systems for this talk. And particularly in the Indian Ocean, it's very interesting for marine life, particularly large whales. So I'm going to show you some spectrograms. Here we have some images of sound. On the y-axis is frequency or pitch, so higher and lower. Across the x-axis we have time, and the colors show the intensity of the sound. So the brighter the color, the brighter or the higher amplitude or the louder the sound we can see. And so what you're seeing here are different blue whale sounds. And basically, blue whales have regional accents, if you will. So depending on where you are in the ocean, you'll hear different things. So on the left, we have something called the Sri Lankan call. You see 3 units there, kind of comprised of different parts. The middle one is known as the Madagascan call. And then the final one are 6 units, a little fainter, of the Antarctic blue whale call, recorded not far off the equator. So we're hearing a lot of diversity across the ocean. Here we have, on the left, another song type which has been attributed to possibly a new population of blue whales. It's not been verified yet, but we're always learning new things. In the middle, we've got some fin whale pulses, the second largest whale in the ocean. And then finally, we've got 3 instances of a sound that's believed to be made by the Amurus whale, a relatively recently discovered species of baleen whale. And baleen whales are the bigger ones, and that's why we can hear them with the international monitoring system, just because of the sampling of the units. As most of you know, the CTBTO's a big strength is the amount of data that are available to us. So here's another spectrogram, an image of sound, but now rather than minutes on the x-axis, we've got years. So we've got 10 years of data here, and if I just show you the small insert, that's the Sri Lankan call. And if you look at it around 100 hertz and 60 hertz on the big image, you might see some faint lines. And that's the Sri Lankan whales appearing over a decade from data from Diego Garcia. So it's really powerful for wildlife monitoring, and that's why it's such a great data set to work on. So what are we trying to do with these data? We would like to turn the recordings into ultimately number of animals, and we need to do some statistics to get us there. And so there are various methods out there to do just that, to estimate these animal absolute densities or abundances, as we call them. And there are terms that you might come across in the literature, such as distance sampling, spatial capture, recapture, and they're very traditional methods for estimating animal abundance and densities, or we have to use other methods using sometimes simulations, which I'll talk about in relation to this project. But all of these methods, their key reason is to estimate the probability of detection. And this is a parameter that we need to estimate that absolute density and abundance. And so if you can see the equation here, it's just multiplication and division ultimately, but there are several bits of the puzzle we need to pull together to estimate that number of animals, big D. So we have little n, the number of detections that we hear in our recordings. C is the false positive proportion. So if we're using automated detection methods, they get that wrong sometimes. So they're not perfect. So that 1 minus C enables us to scale down the number of detections to say, okay, some proportion were not actually whale calls, they were something else. On the bottom, we have pi w squared. That's the area that we're monitoring. We have K, the number of sensors. I'll come back to P. We have T, the time monitored, and then we have R, this Q production rate. How often do these animals make their calls? That enables us to convert call density into animal density. We need to understand the animal behavior. But you'll see probability of detection there appears on the bottom of that equation. And if nothing else, the main point is that if we ignore that parameter or get it wrong, we will bias our density estimates. So all of those pieces are important, but it's important that we think about probability of detecting those sounds. I'll just try and...
Clicker. Can you click the next one?
And so why is detection probability important? Now, this is some data from the Antarctic, and this is seasonal detections of blue whales. And you can see on the y-axis, we've got mean detection rate, so simply calls per hour that we heard on the hydrophone. This isn't CTBTO data. And you can see we have seasonal numbers, and we can see that the highest occurrence seems to be in the winter. We heard more calls. So that, we would start to make biological conclusions about that. But, I think it is. But if we actually then estimated the animal density, the call densities from those same data, you can see what's happened. So we've now accounted for all those parts of the equation I showed you, and the pattern changes. And we can put some uncertainty around those estimates. So the small plot is the one on the left. That's the one I showed you before. That's just the calls that we heard. And then we've gone and estimated call densities. And you can see now it's autumn that's the key season for these animals. And when we did this work, we actually realized that was more in line with what we knew about the animals' migration pattern. So it's more linked to the animals themselves. Turned out in autumn, it was actually noisier. So we didn't hear as much. But when we corrected that through the probability of detection, it turned out autumn was when the animals are most vocally active. So that's why we try and work on these density estimation methods. So with the CTBTO, we're using a simulation-based approach based on the passive sonar equation, so how well the sound travels through the ocean. We're trying to recreate that through a simulation. So to do that, we need to estimate some bearings, some sound propagation models, some noise level measurements, and all of that work is actually coming through the Cortado project that I talked about. And then we also need to make some assumptions about the source level of the animals, how loud they are producing their sounds. And we put all this into a simulation and estimate that probability of detection. Now, there are some assumptions that we make about animal distribution, and one of the summer interns, Victor, worked on that with us this summer. We learned some interesting things. And so we'd like to focus on the Sri Lankan blue whale using data from 2024. We thought that would be a nice case study. I'm showing you data here from 2002, and if you notice that the long tone is about 100 hertz. We've got an interesting thing happening with the whales that's well documented. The pitch of their sounds is getting lower. They're lowering their frequency for reasons we don't fully understand. And so this is data from a previous study over 10 years. You can see it's declining, that Sri Lankan tone that I just referred to. And one of our other interns this summer continued to look at that decline from 2017 onwards using CTBTO data. And we're just working up a small paper on that. And so these results are then informing our automated detector development. We need to know what we're looking for in terms of the right signal frequency to then generate the parts that we need for our equation. And then finally, we do know a little bit about probability of detection using CTBTO data already. It's very interesting oceanography around Diego Garcia in the Indian Ocean. And so basically, if you look one way out from the hydrophone, one of the hydrophones, where we did some propagation modeling into the deep Indian Ocean, you can see some results from our simulation. Probability of detection is on the y-axis, distance is on the x-axis. You can see into the Indian Ocean, our probability of detection decreases very, very quickly, which basically means if we have a whale out in the deep ocean, we won't hear it on the hydrophone at Diego Garcia. However, if we go the other direction, the bathymetry is different, sound propagates better, and so we can hear things out to larger ranges. And so it's really important for us to quantify that when we're turning this into number of sounds or number of animals we're hearing per unit area. So this is all part of the work that's going on at the moment. So finally, this is an example of maximizing these data to look at marine mammal distribution over large spatial and temporal scales. We're using these density estimation methods to basically help us standardize across data sets, so we can then start to compare between sites and across years as different parts of that equation changes. And there are many studies with sparsely distributed instruments, not just the CTBTO IMS, but other ones as well. So the work going on here will help inform other projects too. Thank you very much.
Thank you, Daniel. That's brilliant. Are there any questions from the audience here? Yes, please. Can you stand at the microphone then? Yeah.
Hi, thank you so much for your talk. I was curious, could you talk a little bit more about your process in verifying that these spectral features belong to this type of whale versus something else? Thank you.
It's a good question. What we'd really like is to actually record the sounds next to animals themselves that are producing it. So that's quite a hard biological task, to be out there on the water and see the animal and also record it at the same time. But sometimes, in order to match the sounds with the species of whale making it, that's ultimately what we need. Some of these other studies where we've seen sounds that have features of whale calls, we can compare with other known whale calls and say, well, look, based on this, on these features, we suspect very strongly that it is a blue whale or some other species. But it's not necessarily easy to match call to animal. So there's a lot still to discover, definitely.
If there's no obvious questions there, I have one, which is to ask about, you showed the changing frequency with time. Do you think that's the animals, or do you think that's potentially properties of the ocean? So if the ocean temperature goes up with time or salinity changes, I mean, I can imagine it's really hard to tease out, like, seasonal variability. Is that variability in the ocean, or is it the variability in what the animals are doing, and likewise in these longer-term trends?
Again, we're not sure, and it could be both, or one or the other. So it could be the animals. There's hypotheses that perhaps the animals are now getting bigger and their voices are essentially getting lower. But then also there's been hypotheses about the ocean changing around the animals, and so we're still figuring out what that is. Yeah.
Yes, please.
You talked about the transmission of sound on the different sides in the Indian Ocean. Do you think that affects the behavior of the whales? Do you think that affects how they're able to communicate with one another?
It's also a really good question, and from a behavior point of view, we know relatively very little about these animals, and also they're communicating over big or potentially huge distances. I mean, I was looking at propagation models out to 1,000 kilometers, because that's potentially what the area that's being monitored. And if they're using those features, again, it's still an unknown.
Another question?
About the propagation again. I was just wondering if the blockage on one side is produced by the topography, basically, or is there any other kind of phenomenon that causes this blind sighting?
In this case, it's the topography. So this was using one of the northern sites, and so it was very clear that there was that blockage. But again, I think it's really useful from the biology perspective that we always remember that we have to figure out what area we're listening to. And with acoustics, that's often cannot be straightforward. So as this example showed. So yes, very useful, because actually it changes the conclusions you make about the animals. It's useful for me to know that actually I'm not listening to whales in the deep Indian Ocean. Anything I'm hearing is probably coming from the other side where the sound can propagate better. So it's very important to try and work that out.
Yeah, thanks.
I think we probably need to move on to the next talk. Just before we thank Daniel once again, you can put questions into the chat afterwards. So if there's something you subsequently think about, and we're encouraging the speakers to look afterwards and then hopefully to respond to your questions. So let's thank Daniel once again for a really stimulating talk.